Hey guys, welcome back to the channel. Today we would be learning about an interesting algorithm. This is Tarjans algorithm, which is used to find the bridges in a graph. So we would be looking at what are bridges, then what is Tarjans algorithm, and also we would be solving a problem based on this algorithm. So without any delay, let's get started. First of all, what are bridges in a graph? So let's say we have this graph here. Now a bridge is an edge which connects two components. Okay, so bridge is an edge which connects two components such that upon removal of this edge, like let's say we remove this edge, then the complete component is broken down into two different components. So initially this was whole a component. Now when we remove this edge, so this part become one component and then this part become another component. Similarly, let's say now we remove this edge. So again, this is a single component, then this is another component. So this is also a bridge. Now let's say we remove this edge. So if we remove this edge, then this part is still connected, like 1 and 3 is still connected via this node 2. So this is not a bridge. So now we know what is bridge in a graph. So how we can find such bridges in a graph? So let's start by traversing the nodes, and we'll also maintain a timer. So let's say the timer is t, which is initialized to 1. Okay, so let's start visiting the nodes. So we'll start from 1. So we would arrive at 1 at timing t, which is 1, and the minimum time to reach 1 is 1. Till now the time to reach 1 is 1 and the minimum time is also 1. Okay, so now from 1 we can visit 2. So let's go to 2. So when we go to 2, let's say the timing to visit 2 is 2 and the minimum time is also 2. Now we'll visit 3. So the time to visit 3 is 3 and the minimum time is again 3. Now from 3 we can see that we can go to 1 and we can go to 4. So now we can see that 1 is already visited, like we have already visited 1. But we can see that the timing to visit 1 earlier was 1. So the minimum time to visit 1 earlier was 1. Okay, so we can update our time, like we came here to 3 with minimum time 3, but there is some neighbor who is having time 1. Okay, so let's update its time. So for 3 the minimum time is 1. Now from 3 we can again go to 4. So for 4 let's again maintain the initial time to visit 4 and the minimum time to visit 4. So from 4 again we can go to 5. So for visiting 5 we have time 5 and minimum time is also 5. So from 5 we can visit 6. So the time to visit 6 is 6 and the minimum time is also 6. So from 6 we can visit 7 and the time to visit 7 is 7 and the minimum time is also 7. Great. Now we can see that from 7 we can visit 5. Okay, so we can visit 5, but wait, 5 is already visited and the time to visit 5 earlier was 5. So I can update the timing of 7 from 7 to 5 because there is an edge which is connected to 5, which means that there is a path to go to 5 and that 5 is having timing 5. Okay, so I can update my time. Okay, so 7 can update its time. Now we again came back to 6. We'll just trace back the path which we traversed. So for 6 we have its neighbors as 5 and 7, but we will not consider the parent because the parent will always have the minimum time to reach. So we will never consider this parent of the node. Okay, so another node is 7 which have timing 5. Great, I can update the minimum time to visit 6 as 5. Now again when we come to 5, the time to visit 6 is 5 and 5 is already having minimum time as 5, so we will not change it. Then again we will go to 4. So while tracing the path we came to 4. Then here we see that 4 is having time 4 and 5 is having time 5, but the minimum is 4, so we will not do anything. We'll just go here. While tracing the path we reach to 3. Now at 3 we see that For 3 the timing is 1 and the time which 4 is having is 4. So 3 is already having a minimum time, so no need to update the time. Now for 3 we have already visited 1, so again we'll just go to 2, and here for 2 we can see that the minimum time is 1 of 3 and 2 was having its minimum time as 2. Okay, so we'll just update the time from 2 to 1. Great. Now we'll again go to 1. Now at 1 we can see that 2 is having time 1, 3 is also having 1, and 1 is already having 1, so no need to update. Okay, so now we update all the times. Now let's consider these two bridges and let's try to make some observations. So we can see that the time, which is the minimum time to visit 4, is always greater than the time to visit these nodes, like the nodes in this component, because there is no connection between this component and this component. Why? If there exists a link between this component to this component, then the minimum time to reach 5 would have updated by any of the value from this nodes. So let's say if there is a link from 3 to 5, so this value would have updated to 1. And now for 4, as the neighbor is having minimum time to reach it as 1, so 4 would update its time to 1. But this is not the case. Why? Because simply there is no link from this component to this component which can reduce the time for 4. Hence, this is the main intuition behind this algorithm, that there is only one link from the previous component to the next component and no other link exists. So hence this is a bridge, and similarly for this part we have this one as a whole component and this bridge, because this is not having any edge with the previous component or even here. So hence these are completely two separate components. So now we know the intuition behind the problem. Now let's code this problem. We'll just select this problem, critical connections in a network, which is basically the application of the same algorithm. So here we are given n servers numbered from 0 to n minus 1, which are connected by undirected server to server connections. So which means a bridge forming a network where connection I equal to A to B. This is basically the edge between a node to bit node. Okay, so this represents a connection between server A to B, and any server can reach other server directly or indirectly through the network. Okay, so a critical connection is a connection that if removed will make some servers unable to reach some other server, which means that two networks will become disconnected upon removal of this edge. So yeah, so basically you can go through the problem, but this is the same application of Tarjans algorithm. So we'll just code our Tarjans algorithm. Okay, so let's first initialize the timer. So let's initialize it with 1, and here let's make the name short. Okay, now let's store our connection in some adjacency list. Okay, so we'll just store the list. Let's get the two nodes. We'll just store our bidirectional graph, adj.get u.add v. Similarly for v, we'll store an h to u because this is a bidirectional graph. Okay, so we have our graph ready. Then we'll just maintain two arrays, like the initial time to visit and the minimum time to visit. Okay, so these are for the nodes, and then we'll just maintain a visited array. Okay, so we will also need to store our answer, which will return the bridges. Let's name it as answer. Now this is whole a connected component, so we can just start from 0th node. We'll just pass the visited array, then we will pass our adjacency list, Then let's pass initial time, minimum time. Okay, we'll also need to pass the parent, and then yeah, so we'll just return our answer at the end. Okay, so let's write DFS here now. So okay, the DFS is node, then we have the visited array, then we have adjacency list. Then what else do we have? We have an array which is initial time, then we have an array which is minimum time. Okay, so then we have parent node. Great. What else do we have? Okay, so this is it. Now first we'll mark the node as visited. Okay, so the node is visited. This is simple BFS, and then I'll just mark the initial time to visit the node equal to minimum time to visit the node, which is the timer, and we'll just upgrade our timer, just increase it. Then we'll just go to all the adjacent nodes and let's see if it is visited. If it is not visited, then we will just visit this. Okay, so while visiting, we'll just pass v, then we'll pass the visited array, then adjacency list, initial time, minimum time, parent. Okay, so one thing I forgot to take here, which is our answer. So we'll just quickly take this. Let's extend this a bit. Okay, so we'll just pass our answer here. Now if a node is not visited, we'll just visit it, and after visiting, we'll just mark the minimum time to visit this node, which is node equal to the minimum time to visit our vth node, which is the vth node, and the minimum time to visit this current node. We'll just store the minimum time, right? And then we'll check if minimum time to visit v is still greater than the minimum time, or I would say initial time to visit our node, then there is a problem. So here, this is the part which is bridge, because the initial time to visit 3 is less than the minimum time to visit the next node, because there is no connection, right? So here we found a edge. Great. So we'll just add it into our answer as list of what? List of node and v. Okay, so then if this is already visited, then we'll again calculate the minimum time to visit node, because v is already visited, which means we can mark the minimum time to visit our node. And here one thing which we have to do is, if v is the parent of this node, then just continue, because parent will always have the minimum time to visit. Okay, so we'll just continue, and this is pretty much our code. Let's try to run this. Okay, so what is the problem here? Okay, so adjacent dot get node, so we want the adjacent nodes of this node. Okay, oh, spelling mistake here, I'll just quickly correct it. Okay, let's run this again. Oh, I think I forgot to return the answer. No. Okay, so here it should be void. Yeah, what a silly mistake, man. Yeah, we'll just run this. Oh, so okay, I think I forgot to just initialize this adjacency list, so we'll just initialize this as equal to 0, as less than n, I plus plus, then adj dot add a new list. Okay, so we'll just check our code once. Okay, so this looks good, and then here, so okay, so yeah, the rest of the things looks good to me. Okay, so I'm passing the parent here, but this should not be the case. Instead, we should pass the node, and let's quickly run this. So yeah, it gets accepted. So let's submit this. Okay, so thanks for watching, and subscribe to the channel for more such videos.